Okay, in this video, we'll continue our discussion of binary search trees. And we're building up some concepts that we're going to need in order to implement a removal of a node from a tree. And that concept in this case is the idea of a successor. And since it's closely associated with predecessor, we'll just talk about both of them at the same time. Okay, so we know that a binary search tree imposes an ordering among the nodes. Right? So if our tree looks like this, where 9 is the root, then in reality, when we look at the values, the ordering goes something like this: 1, 3, 4, 5, 7, 8, 9, 15, 15, 16, 19. So this example, I'm assuming a multi-set, but everything we're going to talk about applies whether we're talking about multi-sets or normal sets. Okay, so you notice the ordering has this weird shape through the tree. And that's to be expected because of the way the binary search tree works and the fact that when we insert nodes, we're not inserting them in order, but we're placing them in order somewhere in the tree. So when we look at a tree like that, a concept we need to think carefully about is this idea of successor. A successor node is the next larger node, and a predecessor node is the next smaller node. So if we look back at this tree, then 1 is the predecessor of 3 because it comes immediately before 3, and there's no node that would be ordered between 1 and 3. Likewise, 3 is the successor of 1, coming immediately after 1. Kind of a trickier case is that 9 is the successor node of 8, right? Because the next larger node from 8 is way up here at the root. Even though 8's a leaf node, 9 is its successor because there's nothing that comes between them. And in this case, where I have a duplicate node, 15 is the successor of 15. And coming back over here, we see that 4 is the predecessor of 5, and 5 is the successor of 4. Right, so this predecessor-successor relationship, it doesn't necessarily follow a parent-child behavior. It can follow parent-child, like 3 to 4 is parent-child, but 4 to 5 obviously is not. So successor-predecessor is not quite so simple as these simple parent-child relationships. We have to think a little more carefully about it to define where is a node successor or where is a node's predecessor. So there are a couple of cases we can pin down for finding a successor for a node. And predecessor is just kind of the reverse of this, kind of the opposite of this. So I'm not going to talk about it by itself. Okay, so when we consider node n and we want to find its successor, then if n has a right child, then the successor should be to its right? It should be one in its right subtree. And the successor in that case would be the smallest node in its right subtree. And another way of saying the smallest node would be to say the leftmost node, because it would be the node on the farthest left on that subtree. So if a node n has a right child, then its successor is the leftmost node on its right subtree. Now, if a node has no right child, then the only possibility at that point is for it to have a successor higher up in the tree. And so what we have to do in that case is go up the tree until you find an ancestor such that n falls in the left subtree of that ancestor. And then when you find that ancestor, then it's the successor of the node you started from. And if it turns out that there's no such ancestor, then that means there is no successor. Let's take a look at these cases, case 1 and case 2. So for 5 has a right subtree, and that means 7 is the successor of 5. In this case, 7 is the leftmost node of the subtree of 5 because it has no left children, and that makes 7 the leftmost thing here. Another example would be if we look at 9, 9 has a right subtree, and then 12 is the leftmost node under 9. So 12 is the successor of 9. An example of case 2 is over here. When we look at node 7 and we want to know its successor, it has nothing in its right subtree. That means that if it has a greater node somewhere, it has to be above it. And so we go up and we go up, and eventually we find 9, and we see that 7 is to the left of 9, and that means 9 has to be bigger, and so 9 would be the successor. It's the first ancestor we reach that's bigger than 7. But, and then likewise over here, 12 has no right subtree, and when we go up, we'll find 15. However, if we were to ask this same question of 16, what's 16 successor? Then 16 has nothing in its right subtree, and when we go up looking for an ancestor for 16, we never find an ancestor on its, that it would be on the left side of. And so we would go all the way up the tree to the root and then realize, oh, 16 has no successor. 16 is the biggest value in that tree, and so it can't have a successor. Okay, so if we had to implement this in code, there is, we would need a little bit of help. It's easy to look down a tree, but it's not easy to go back up, right? So far, we've only described nodes as having children, as pointers to children. And we know from our work on linked lists that you can only really go in the direction of the links. You can't go in reverse very easily. Of course, what we could do is keep a stack of nodes as we go down a tree to make it easy to return. That'd be one possibility if we need to find an ancestor that's above us. Or another way we could find an ancestor that's above us is we could change each node to have a pointer to its parent. So it's kind of like a doubly linked list. We could have a doubly linked tree in which parents point to children and children point back to parents. And then if we're at a node and we need to go up to find an ancestor, we can just traverse the parent nodes back up the tree to find a parent node as needed. And so we would add to our BT node class that we saw earlier, we could add a field called parent that would point back to its parent node. Okay, so in summary, a successor node is the next larger node in a binary search tree. A predecessor is the opposite, it's the next smaller node. And it's important to keep in mind that the successor or predecessor may not be a child of the node. In fact, it may require searching deeper below it, right? It might require finding the leftmost node of its right subtree, or it may require walking up the ancestors until we find one, in the case of successor, that's larger than the node we started from.